Good evening. I'm Alexander. I'm the executive director here at the Long Now Foundation. And as many of you know, we start these talks with a long short, a short film about long-term thinking. And tonight's one is one that I chose a long time ago and been waiting for the perfect talk to do it in. And while Sarah's going to be speaking tonight about exoplanets, planets in systems very, very far away from ours, this film, The Wanderers, is an amazing piece that shows how much more discovery and exploration we can do of some of the worlds in the nearer space. Thank you.
I feel like I should walk on here with something other than boring old 1G. Hi, I'm Stuart Brand from the Long Now Foundation. I learned about planetary atmospheres in the 70s. Because Coevolution Quarterly, which I edited then, was the first US publication to publish the Gaia hypothesis by Lynn Margulis and James Lovelock. And Jim tells the origin story of the Gaia hypothesis that he had been hired by Viking as a atmospheric chemist to develop the electron capture device that was detecting ozone at parts per million and DDT at parts per million and so on. And they asked him to look at basically spectral information coming from the atmosphere of Mars and tell him if there was anything interesting about it. And he said, well, the interesting thing about it is it's in perfect chemical stability, which means there's no life on Mars, sorry to say. At which point NASA said, that's very interesting. You can be quiet about that now. And he was, but it made him realize that the extremely unstable chemistry of Earth was a signal not only of life, but of some processes he began looking at and how it's become Earth system sciences. Looking at the presence or absence of life on planets is an atmospheric issue. So it'd be nice to get somebody to talk about it who's written a book called Exoplanet Atmospheres. Sara Seager.
Thanks, Stuart. Thanks, everyone, for coming out. Well, the funny thing about atmospheres is that even when we think we understand them in a global sense, there's a lot of small things that don't always make sense. This year in Boston in winter, we got over 100 inches of snow, which for us was great. It was a record. But the funny thing is coming out here, it's way colder than it is in Boston. So here we are with a view of the night sky. And I wanted to just start out by reminding all of us that every star in the sky is the sun. And if our sun has planets, surely all these other stars should have planets also, and they do. And in the last 20 years or so, we have found thousands of planets. And we believe now that every star in our sky has at least one planet. And planetary systems are just so common. Whenever I look up at the stars, I always wonder, is there another planet around that star? And are there any intelligent beings on that other planet far away looking back at us? I really hope they're out there, and I hope that someday we're going to find them. And so what we're looking for when we talk about looking for another planet that might be like Earth is looking for Earth, a pale blue dot, far away. And this is actually a real photograph of Earth by the Voyager 1 spacecraft. This was orchestrated by Carl Sagan, and it was taken from 4 billion miles away. And believe it or not, most of my work about atmospheres, it is about how to take a little dot like this, whether it's a star or a planet, and in the future another Earth, and try to infer everything possible about that planet, whether there's water on it or signs of life by way of gases in the atmosphere that don't belong. So what I'm going to talk about today is what is an exoplanet? When and how will we find another Earth? Can we go there? If we can't go there, why look? And by the way, these are the questions that I get asked most often by people of all walks of life, from children to elderly people to people I meet on the plane, to actually everyone. And you know what the most popular question is? It is, can we go there? And even when I explain it, how we can't really do that right now, I still get asked it over and over again, even during Q&A. So I'm sure some of you are wondering about that. Now, to get started, I wanted to leave you with something to take away. When you get home tonight or in the coming days, I want you to Google for Eyes on Exoplanets and download this software. I didn't write this, or I wasn't part of it. I just love it so much. I have a little clip of it to show you. And it starts out here with an artist's illustration of what we think our Milky Way galaxy looks like from far away. A galaxy is a collection of bound stars, and our sun would be about here with respect to the billions of stars in our galaxy. And this is just a little clip showing you our Milky Way, and these zooming into where our sun is. You can see the stars here, and all the highlighted objects are stars with known planets. The different stars are different colors. Red is a small star, yellow would be like our sun, white would be something brighter than our sun. And now this clip just keeps zooming in to our planet Earth. It actually also shows you some spacecraft that are orbiting our sun. Epoxy's here, you can see Spitzer and Kepler. Now you can use this software, and here we're going to click on the west coast of North America, looking up at the spring night sky. and overlaying the constellations here. Actually, you could actually do this now if you download this software for tonight or anywhere on Earth where it's dark at that present time, and look up at the sky, and it'll show you a real map of the stars. Now here it's overlaying the constellations, of course. Those are not conveniently drawn for you out in the sky. And also, many of these stars, you couldn't see them just with your naked eye. You'd probably need binoculars or a telescope. You can see this is going to actually now rotate to zoom into a very special part of the sky. Look at that. Does anyone know which part of the sky this is? Yeah, this is the Kepler Space Telescope's field of view. And there's such a concentration here. Actually, the whole sky really, that's when I said that we think every star in the sky should have a planet, because we actually know that from a specific technique called microlensing. But on the whole, there are a lot of planets out there. Now, the thing that's really nice about this software is you can actually use it to search for a planet by name, in case you happen to have a favorite planet whose name you know. One of the favorites from astronomers or the public or anyone really is Kepler 186.6. And if you zoom on it, it'll actually take you to this, in this real map of the stars, where Kepler 186 is, and you can take a kind of a look at it and its orbit. Now, this particular system has several planets, but the reason we're excited about it is the so-called Kepler 186f in the planet's habitable zone. Now here you see the habitable zone is shaded. We don't know exactly where it is, but what the habitable zone is it's a region around a star where if a planet is in that orbit, it will be heated by the star, not too hot, not too cold, but just right for life. And now in this movie clip, it'll keep zooming in on Kepler 186f. But here's where the fine print, you can barely read it, it says, hypothetical visualization of planet. We don't know this. This is the part we don't know. We know about the real map of the stars, but we don't really see planets in that level of detail quite yet, actually. Actually, we might never do that in our lifetimes. But that's the software, and it's called Eyes on Exoplanets, and you can spend a lot of time clicking on the stars and fooling around with it, and I really hope you all are able to do that. But not now during my talk. So actually what I work on is planet atmospheres and what planets look like from far away, and I write computer code, and all my students also do. But before I get to some more details, I wanted to just take you on a tour of some of our favorite planets. So here's a poster, actually, Kepler 186f. Yeah, it's a travel poster. And here it says, well, Kepler 186f, where the grass is always redder on the other side. Because Kepler 186 is a small star, it's a red dwarf star, and some people actually have worked on this, thinking that perhaps plants and vegetation is a different color, taking advantage of different wavelengths of light that the red star would be brighter at than our sun. Next travel poster is for Experience the Gravity of HD 40307G, a super-Earth. And here they're showing someone parachuting, but here in this case, the planet has a surface gravity of about 1.5 times the size of Earth. Kepler Relax on Kepler 16b, the land of two suns, where your shadow always has company. And this particular poster is showing an astronaut on a planet that's orbiting two suns. We call these circumbinary planets, and now we know of about a dozen of them. It's a planet that orbits two suns. And actually, as long as those two suns are close together and the planet is several times further away than that distance between the two suns, it should be gravitationally bound. And what I like about this is, well, science fiction got some things right. One of my favorite planets is Kepler 10b. This is what we call a hot super-Earth. It is so close to its sun that it's based on Kepler's law. The closer a planet is to a star, the shorter its orbit, the faster it orbits. And this planet orbits the sun entirely in less than 1 Earth day, zipping around that sun. The planet is so close to the sun that as heated by the sun, the surface would be so hot, we think hot enough to melt rock. And in this artist's conception here, they're showing you just that the cracks and it would be like going outside and instead of seeing a puddle of water, it would be a puddle of rock. Only we could never go there because we would melt long before we reach the surface. Now, the last one I'll tell you about is Gliese 1214b. In this particular one, you can see the nebulosity, because the artists think this was too boring to just show you the planet with the star. And in this case, we actually don't know much about this particular planet. We know about its mass and its size, and we don't know a lot else about it, actually. And most of these planets, we just know their mass and size and the amount of energy reaching the surface. But this planet is of interest because it falls in a very intermediate mass and size range, actually. It's too big to be an Earth, but way too small to be a Jupiter, and even too small to be like a Neptune. And what that means is that this particular object, it actually has no solar system counterpart. And we don't even really know what this planet is made of, Gliese 1214b. It could be a big rocky planet surrounded by a massive gas envelope. Or it could be something we think about, we call it a water world, a planet that would be like one of Jupiter's icy moons, 50% water mass or more, a scaled up version of that. And if this planet was predominantly water, actually we think it's pretty close to the star, it's pretty hot, that it would have a thick steam atmosphere. And under that atmosphere wouldn't be a layer of liquid water, but would be a layer of supercritical water, a kind of material that's not quite a gas, not quite a liquid. And that would actually be over a high version of high pressure ice. I would say like Ice 9, but no, Ice 9 was just a joke in the novel. Not a joke, not serious, but these high pressure ices, it's where water is squeezed together until it becomes solid. So all sorts of different types of materials inside planets could be out there. And I just wanted you to know that there are lots and lots of planets. This graph is showing you all the planets found by the Kepler Space Telescope to date, as of July 2015. And what you're seeing here is the size relative to Earth radius. So Earth would be here at 1 Earth radius. And at the bottom here, it's just telling you about the planet's orbit, orbital period in days. So this would be a planet of 1 day. Out here at 365, you'd have Earth. But just look how many there are. There's thousands of planets out there, and those are the only ones we even know about. And I want you to take a look at this graph, and you can actually think for a moment and see where's the graph the most dense? Where are the most points? I'm trying to ask you, can you see what is the most common planet size? And on this plot, you can see it's sparsely populated up here. In fact, so these Jupiter-sized planets are not nearly as common as planets down the size of Earth or a little bit bigger, actually. And this is one of the biggest findings, actually, in exoplanets. And I'm guessing you don't hear about this. Many of you wouldn't have heard of this at all, but the most common type of planet out there is something small. And this is really puzzling, actually, because all the things that we were taught, at least in planetary science, is that the end product of planet formation should be a big planet like Jupiter, where Jupiter is born and material accretes until it gets massive enough to, like a giant vacuum cleaner, just suck in all the material around it until it exhausts its feeding zone. And we always believed that the end product of planet formation would be a big planet, as big as it could possibly be. But in fact, it's not true. And for many of these planets in here, about 2 to 3 times the size of Earth, Neptune is up here at 4 Earth radii, we actually don't know how those planets formed. And so we're left with this kind of really big puzzle from exoplanets. Now, out of all the planets we're looking for, the ones we want to find to, in the future, be able to search for life on them are the so-called Goldilocks planets. Planets that orbit from the star. They're not too hot, not too cold, but just right. And this is a little complicated. I'll come back to this a little bit later, but it's the so-called habitable zone or Goldilocks zone. So what is an exoplanet? A planet that orbits a star other than the sun. Thousands of exoplanets are known to exist, and we expect that nearly every star has a planetary system. All right, how and when will we find another Earth? Well, it turns out that our Earth is very, very hard to find. And we actually use this analogy that looking for an Earth would be like looking for a firefly next to a searchlight. But that firefly and searchlight would be thousands of miles away, like the distance from here to Boston. Usually I'm working in reverse. I'm usually on the East Coast. I have to say it's like looking here. But think about that for a moment. A firefly, our Earth compared to our sun, is 10 billion times fainter. That's such a huge number. And I want you to think about for a moment, what could you, in turn to think of 1 to 10 billion, what could you buy for $1? It's like actually not a whole lot nowadays. And now think for a moment, what could you get for 10 billion? I mean, it's such a huge number. Our Earth is so faint compared to our sun. That's our analogy here. And I want to tell you a bit about this picture where a number of years ago I was consulting for National Geographic. And they actually wanted to take a real picture of this. Anyone here who's a photographer? I think you know. You don't really have the dynamic range to detect the firefly next to the searchlight. They fudged it, I think you can see here, the firefly. And the first thing, it was my job to tell them what I liked or what I didn't like or what was right or what was inaccurate. And the first thing I said, which was inaccurate, was the searchlights here. Look how they're all together. They actually rented the searchlights and took it to a field and made this picture. And I just said, look, we don't see stars like this. You never see 4 stars together. Nonetheless, I think you all know what a great publication National Geographic is. And the photographers came back and they were amazed. They were so excited, jumping up and down. And they said, well, we couldn't take a picture of the firefly next to the searchlight, but we could take a picture of the firefly in front of the searchlight. And they actually had inadvertently discovered a whole different way to find planets. We already knew how to do this, but they had found it on their own. It's called transits. And how many of you have heard of transits? Okay, so I'm going to explain for those of you who don't know, but basically, if you have a planet going in front of a star, instead of being a 1 part in 10 billion difference, it's only, well, I will say only 1 part in 10,000. For an Earth going in front of the star, it signals 1 part in 10,000. And if we can get a big Earth going in front of a small star, then that's only 1 part in 1,000. And that's a much easier number to handle, actually, for any kind of measurement. And so to tell you what a transit is, and why today we're always focusing on transits, it's just an easier thing to see than a planet directly. So here's showing you a planet. Can you all see the little planet going in front of the sun? It's supposed to be Earth-size compared to our sun. We don't see any other stars other than our sun spatially resolved like this. And there it is. And look at the bottom here. There's a graph of the planet going in front of the star. And when the planet finishes going in front of the star, that drop in brightness goes away. So I'm going to show that to you one more time because this is actually the way that we find most planets today. They're found by the so-called transit method. And just in case this plot made it look too easy, you know what? It's at least 10,000 hours per planet. Yes, because we look at lots, we meaning the whole community, has lots of data looking at hundreds of thousands of stars, searching all of them just for this very special signature of a planet going in front of a star that works on the right time scale and is the right drop in brightness. And even then, many other things could mimic the planet. So I'm going to show you some real transit, we call them transit light curves. And here you can see this is just time in hours. And these are all giant planets. The transit lasts for a few hours. This is a few hours in here. And it's also showing you the size of the planet compared to the size of the star and where the planet is crossing on the star. And actually, you can see they're all different. Sometimes people would call this like a family portrait. And they all look a little different. They're different sizes compared to the star. They transit a different part. And so now I just have to show a few more technical slides because I was thinking some of you do know about exoplanets. And some of you may have heard in the news about 2 weeks ago, there's a planet called Kepler 452b. And so, yeah, some of you have read about that. So I was just going to shed a little light on it. First, that's the artist's conception, which you would have seen in the news. And I want to show you what the real data looks like. And here is Kepler 452b. This is, so if you don't understand the next two slides, you don't have to understand the rest. You don't have to understand them to understand the rest of the talk, but I just wanted to give you something to chew on. So this is days, actually. And this is like 200 days, 400 days, out to 1,400 days. So this is a few years of data. Kepler Space Telescope looked at that one patch of sky for 4 years. And all of these are points of data taken by the telescope. And so remember, we're looking for a star that's constant brightness and time and looking for a tiny little drop that signifies a planet. Now, I don't know if any of you can see that drop on here. First of all, you know what these gaps are? It's when the spacecraft wasn't taking data. Sometimes it had a problem and went into safe mode where it didn't do anything. Other times when it was downlinking data to Earth, Kepler couldn't take data. It actually had to rotate 4 times a year so the solar panels would be pointing the right way. Actually, you know what's really funny is they gave you a little signal here where the triangles are. You can't see it, actually. You can't see it in the data. And indeed, computers would search for it. We wouldn't do this by eye, although initially people looked at the data by eye. And when the computer finds a signal, a drop in brightness, it will bin the data together. It will take all that data and fold it onto the same period and phase. And here's what the transit light curve looks like. So this is what it looks like. So the detection went from the space telescope taking data for 4 years, using computer algorithms to search for these little tiny drops in brightness and putting the data all together to get this little tiny drop in brightness. And this here is several hours, and this little drop here looks like it's just about, let's say, 100 parts per million. But in my one more technical slide, this planet was claimed to be the most Earth-like planet ever found. That meant it's about the size of Earth, a little bigger, and it's receiving about the same amount of energy from its star. So just for those of you, this is my last kind of technical slide. This is planet size compared to Earth size, and this is the amount of, at the bottom, it's showing you the amount of energy compared to our sun. So Earth would be down here, right at the bottom of the graph, at 1, Earth size. And this other planet, we don't know this is what I wanted to convey to you. We do not know the planet's exact size. We do not know exactly how much energy from the star is hitting the planet. All we know is that the planet could be any size and any amount of energy from the star hitting the planet in this box here, in this oval rather. And so here's where the habitable zone is for this particular planet. So if we could make a better measurement and found that the planet was here, it would be way too big and way too hot to be habitable. So this was just a more complicated way of saying we don't know everything about the planet, actually. We only know the size and approximate. We know the size with some uncertainty, and we know about how much energy is hitting from the star, hitting the planet's top of its atmosphere, also with some uncertainty. So what we'd like to do is find planets around stars that we can study in more detail. And what we're going to do next is, in the search for other Earths, we're looking for transiting planets. And I want you to know that there are stars actually of all different sizes. There are these giant stars, really huge. The yellow one is like our sun. It's just a cartoon diagram to show you all these different stars' sizes to scale. There's this red giant, which is a hugely evolved star. And now look at this little planet I stuck on here. This is about the size of Earth. This would be the size of our sun. And now look at this red dwarf star, a small star, very common type of star in our galaxy. Now look at that planet. Do you think that planet's the same size? You know, it is the same size because I just cut and paste, but it looks so much bigger here. Look how much bigger it looks. I'm just trying to show you that actually that planet is blocking out so much more of the star, the small star, compared to the sun. And so actually what we're going to do in the search for another Earth is we actually will combine the most favorable planet finding technique, transits, for the smallest planets and the most favorable star type. So that's our way to go forward, actually. It's to look for a big Earth or an Earth-sized planet transiting a small star. So in this case, we're not going to find like a true Earth twin. It's more like an Earth cousin. But let me actually describe it a little more by taking you on a virtual trip to this small planet transiting a small star. First of all, that small star has a much lower luminosity output than our sun. And imagine for a moment like standing near a fire. If the fire is really small, you have to get closer to it for the same amount of warmth compared to a bigger fire. So for these small planets orbiting small stars, the habitable zone is much closer to the star. And so in this case, if we were to be able to visit this planet, actually the sun would be very big in the sky, huge like this. And this artist who made this image also is showing you other planets in the same system. And the artist also used the artist's license to make it a red sky with purple clouds. Now, on this planet, believe it or not, that the planets that are close to the star, because of tidal forces from the star, it turns out we believe that most of these planets would show the same face to the star at all times, just like the moon shows the same face to Earth. So that means that every time it rotates once, it goes around the star once. So 1 year is equal to 1 day, actually. But what this would mean for us if we were visiting the planet is that the star, or the sun, would always be in the same place in the sky at all times. So you could choose to vacation where it's always daytime and sunny. Or you could choose, for the astronomers, you would choose to go where it's always dark. But actually, you might want to go where the sun is always setting, because that would be permanent. Now, if you're on this planet, for any children who might be in the audience, the good thing about this is the year is so short because the planet is close to the star, and because of Kepler's law, a closer planet orbits more quickly, depending on the mass of the star. And so in this particular example I chose, that planet would be orbiting the star about every 20 days. So you'd have your birthday every 20 days. But that wouldn't be so great for the parents. Okay, now, if we were to be able to visit the so-called small planet transiting the small star, it actually may not be so great after all, because these red dwarf stars tend to have a lot of flares. They're very active. They have a lot of activity. And that means that if you're using your phone or any electronics, it may get knocked out. And it wouldn't be so great maybe for us if we could visit, because all those UV rays coming from these M stars are very active. It'd be very bad for our health. So we'd probably have to go to the dark side. And I want you to know that over the years, a lot of scientists go back and forth. They've complained about these planets. Well, if it's tidally locked, one side is getting heated, the other side is cold. This could be a real problem for the atmosphere. It wouldn't be, though. The atmosphere would circulate the energy. Or they'd say, well, it's so close to the star, it might not be able to get water delivered to it from asteroids, but we're not worried about that. And the reason is because it's really just a great shortcut. A shortcut to Earth 2.0 is finding a super Earth, like a big Earth, transiting a small star. And how will we find another Earth? Just to summarize, we'll use transits. It's the most favorable planet finding technique. We'll search small stars with the habitable zones close to the star, and we'll consider super Earths. So actually, I just want to share with you something you may not know about. It's called Transiting Exoplanet Survey Telescope, or TESS. And TESS is an MIT-led NASA mission. It's going to launch in 2017. And it builds upon the Kepler, the pioneering Kepler Space Telescope. And TESS actually, what it's going to do actually is find, it should find a few more thousand planets actually. But number is, we're not really necessarily interested in quantity, we want quality. And we want to find those small planets transiting those small stars so that we can look at their atmospheres later. And we'll do that with another telescope called the James Webb Space Telescope. So I just have a couple of pictures about TESS. It's actually one of my main jobs now is to work on the TESS Science Center. And here's actually a model of TESS. It's actually not that big, right? It's about a big industrial washing machine. Here's the PI, George Ricker. That's myself. Here's another physics professor. Here's the deputy PI, Roland Vanderspecht. And this here you can see the antenna. This is just a spacecraft bus. But inside that bus actually are 4 basically identical cameras. Think of this like a glorified telephoto lens. And to show you a picture of the lens, this, you put your smallest person in the photograph so that the lens looks really big. Actually, what it is a giant baffle. And this camera here, it's just a lens with a special CCD detector. And this was one of the examples. We had to build a prototype and test it, shake it, like to see if it would withstand the launch, the vibrations from launch, and heat it, thermal cycle it, heat it and cool it and heat it and cool it to see if it could survive. And this was actually at NASA headquarters a few years ago when we had our final presentation for which we won the competition to get selected. Okay, so let's see what else I can tell you about this. It's about a 100 millimeter effective pupil diameter. And the bandpass would be all of visible wavelengths, actually. It's a special camera, though. You wouldn't just get this at the store. It's specially designed to be athermal and not to have any, you probably don't notice this if you remember your camera, from, let's say, the old days. It could have vignetting or weird behavior at the edges. This is made to not have that, actually, because we want to get as much great quality data as we can. So how and when will we find Earth 2.0? Well, we really think we have a plan for it. It's the whole community. NASA will launch a telescope in 2017. It's an all-sky survey for these big Earths transiting small stars. If this Earth exists out there around a small star, we have the capability to find it and identify it by the 2020s. And in a moment, I'm going to come back and tell you a bit more about atmospheres and other things about planets. But I wanted to next get to this kind of follow-on question. Well, if we do find a planet and look at its atmosphere and see that it looks interesting, can we go there? Okay, so to talk about that, it's worthwhile to think about distances in our solar system and beyond. And here's a real photograph of our sun. How big do you think Earth would be compared to this image? This actually is a sunspot, and it's about the size of Earth. Actually, I had to search to find the right photo, but this one does the job. The next question is, imagine the sun is this size and the Earth is that size, where would you think Earth would be? Physically speaking, if we were to make a model of our Earth-Sun distance to scale. Why don't you raise your hand if you think you're where the Earth would be? It's a bit of a trick question. Okay, well, it turns out that Earth actually is about 100 sun diameters away from the sun. So if you just think of this, that was just a lucky coincidence, actually. But if we just imagine 100 suns now, I think it would be outside of this room, probably out on the street somewhere, maybe a couple blocks away. So that's how far Earth would be from the sun. Now for a moment, we have to, I want you to imagine if this is our sun, and that's to scale, where would the next star be? This one actually I'd have to calculate because I didn't realize the sun was going to be this big on the screen. So I should probably answer that one myself. I would have to guess it would be about, let's see. Sometimes I forget what city I'm in, because I travel so much now. That's not true. Let me think for a second. I think I'd have to put this somewhere in Russia. Russia's big enough to give me an area of uncertainty. Far, far, far. Okay, so the point is that stars are very far apart. Most of space is empty, actually. And Alpha Centauri, our nearest star system, is 4.22 light years away. So actually, it's far. And Voyager 1 would take over 70,000 years to reach the nearest star if it was pointed in the right direction. So that's a really long time. But I was saying that because I was just thinking how to phrase the next part where, it used to have this huge giggle factor. Someday let's try to go to a nearby star. But you know what, actually? That is slowly going away, actually. And even just this afternoon, I met with some colleagues, and people are really getting ready for this. We want to look for planets around Alpha Centauri. If there's a planet there, we believe someone will figure out how to get there. And that will be longer than 100 years that it's going to take to build the clock, but I think it's going to happen, actually. And I don't know how. I don't know exactly how. I just know that the drive to go there is so strong. And in fact, some people think, engineers that are alive now on this planet, that we could find a way to go, let's say, to 10th the speed of light, that is kind of within reach at some point. Now let's imagine for a moment that that's the case. Let's see, that would take about, if we could travel at the 10th the speed of light, it would take about 40 years to get to the nearest star. That doesn't include speeding up or slowing down. But nonetheless, I was wondering if there's anyone in this audience, think about how old you would be 40 years from now if you would actually consider making the trip, should we say that we had a way to go there? I mean, actually, every single time people would go. And I always have to say, because I always forget to say, well, it would be a one-way trip. And would you still go? And yes, actually, everywhere people have this desire to go. So although we can't go there now, I no longer say it'll never happen. I think sometime it will happen. It will be galvanized when we find a planet around Alpha Centauri. So can we go there? Not for now. Okay, if we can't go there, why look? And now I get to part of my favorite part of the talk. I call it the real search for alien life. And this is what I work on. This is my main reason, my favorite thing when I get to work on research, and it's about the search for gases in an exoplanet atmosphere that might be attributed to life. But first, science fiction said we have to travel, it's so funny because in science fiction, they always said we had to travel there, like the Enterprise would have to travel at great distances and incredible speeds to get in orbit around an alien world so that Spock could analyze if the atmosphere is habitable and if there were life forms on the planet. And the thing is that, they never thought, well, why don't we just build like a ginormous telescope and look from far away? And we don't know actually if they did that or not, but it would have been a pretty boring show if they just did that. So, we don't have to figure out warp speed, and I hate to dissuade any of the junior engineers, but right now we do that actually. We observe planets from far away, and here's a real photograph of the Hubble Space Telescope, which we use, and we, meaning the community, uses. And this actually was a real photo taken by the departing Space Shuttle Atlantis after it did a final servicing mission to Hubble. And Hubble, actually, we use it to study planet atmospheres. And I just want you to know that although we don't observe small planet atmospheres yet, we do not see anything like an Earth-sized planet atmosphere. We have studied giant planet atmospheres, hot giant planets. They're the easiest atmospheres to study. They're big, hot atmospheres. They have water vapor and other things in it that makes it easy. And so I'm just going to spend a few minutes telling you about what we're looking for and why and how it all works, so you can have something to take away. Well, here's a picture of a rainbow. And I hope everyone here has got to see a rainbow at some point. But in this rainbow, what you probably haven't seen, though, because if you look at the rainbow in a lot of detail, you could actually see that some colors are missing. Some parts of these colors are actually missing. And if we actually take the sun's light and spread it out, not by refraction in a raindrop, but by a special instrument called a spectrograph, we'd actually see this. And here you see little tiny parts are missing, actually. And these are due to absorption, either in the sun's atmosphere or the Earth's atmosphere or both. And I want you to see here, there's very different lines missing. See, this is a really big one. There's some very thin ones. And they're all over the place, actually. And each atom and molecule has a special set of lines that it absorbs. And these missing colors, it's absorption by gases in the atmosphere. And it's been studied for many decades. We're still studying it now, actually. And you can either measure it in the lab, or other people can do very complicated computer quantum mechanical calculations, because each molecule has a specific fingerprint in each atom. And you can actually work out what all of these lines are actually. There are a few things we don't know, and actually I was just reading today on the way over on the plane. There are these things called the diffuse interstellar bands that even in between stars there's a tiny, tiny bit of gas, and there's some things we don't know what they are actually. And they'd finally identified these bands due to like a buckyball, a giant form of carbon. So anyway, this is the atmosphere, and I wanted you to know that so we call the spectra are required to identify a planet as Earth-like, because Earth and Venus are about the same size and about the same mass. And they fall in that, remember that uncertain habitable zone? I showed you the graph. We don't totally know where, if like Kepler 452b, we're not so sure of all the parameters. So Earth and Venus would basically be identical to any planet search technique today. And unless we can get a spectrum and identify the gases in the atmosphere, we need to be able to move forward by looking for gases in the planet atmosphere. I just have to pause for a second and ask if anyone was keeping track of time. Stuart, were you keeping track of the time? Because I didn't notice what time we started, so. Okay. You're good. Okay. So, all right, so the question is, what gases should we be looking for in another planet? And here we have, on our own Earth, we have studied it literally in every type of detail you could imagine. On our own planet Earth, oxygen is our best biosignature gas. We think that on our planet, we know on our planet that oxygen fills our atmosphere to 20% by volume. And without life, without photosynthetic plants and photosynthetic bacteria, there would be virtually no oxygen. And so oxygen is filling our atmosphere to 20% by volume, and that is what we call our most robust biosignature gas, because it's such a highly reactive gas. It shouldn't actually last in our atmosphere at all, really. It shouldn't be there, actually. And we have other gases too we like methane, nitrous oxide. We actually have a whole list of gases here. We have things called dimethyl sulfide and methyl chloride. We're kind of slowly working our way through, trying literally to exhaust every possible molecule that might be produced by life. It turns out that even when you walk through the pine forest and those chemicals coming off of trees that makes it smell so nice, those technically are biosignatures. They're just produced in such tiny quantities that we can't see them from far away. So there's this huge kind of branch of research that's just starting to flourish now about what types of gases should we be looking for on planets far away. And we can come back to that in the Q&A if you have more specific questions about that. So if we can't go there, why look? We call it remote sensing, to search for gases in a planet atmosphere that might be attributed to life. And this is actually a really, really hard problem, because although we've observed several exoplanet atmospheres already, giant planets, we mostly understand what we're seeing. This whole thing about finding life is a real challenge. And we've made it all sound so easy up till now, if you've ever heard about this or just looking for gases far away. Oxygen is so great. But actually, almost any other gas other than oxygen, we have to assess whether it is present in levels so far out of equilibrium that it shouldn't be there. And then we have to try to rule out every single possibility before we can even say it might be made by life. But the problem we're facing is that, unlike that earlier example, we don't really know what the equilibrium state is. When you say we want to find a gas that is so far out of equilibrium, because planets are complicated. Gases are coming out of the surface. The star has ultraviolet radiation, the same thing that creates smog in our cities. It's also creating chemicals. And so we're really trying to work out every last possibility. We're working hard on it now. So for the last part of my talk, I actually have to tell you about something that is really probably one of the more exciting things going on right now. But I have to let you know that transits are only the first part of a long story. Because these transits, when the planet goes in front of the star and the starlight drops in that tiny amount, it's only possible for very perfectly aligned planetary systems. Okay, we think that all planets, all stars are born in a random way. That means that their rotation axis could be in any direction. It's just a random part of how the ball of gas that collapses to form a star actually ends up being. And it just means that the planet's orbit could be like this, or any way. It won't necessarily transit. And in fact, for an Earth, the chance to transit for an Earth at Earth's distance from our sun, around another sun-like star, is just 1 part in 200. And so if we want to find the nearby Earths, the ones someday we might go to, the ones that will be bright enough for us to study their atmospheres, we actually have to do a whole different technique. And that comes back to that firefly analogy, where the star is so bright that the glare is bleeding all over the detector. We need to find a way to block out the starlight so we can see the planets directly. And here there were conveniently 3 planets. So we call that direct imaging, where we will block out the starlight and see the planet directly. Now there's a main challenge here in blocking out starlight, and that has to do with the laws of physics called diffraction. And here I'm showing you a circle. Imagine that your telescope mirror is this. Actually, imagine that we're blocking out the starlight by like a giant screen in space. That's a perfect circle. You'd think we would just block out the starlight perfectly, but that's not what would happen. Actually, we would see this ringing pattern called airy rings. And this analogy, I want you to think about light being like a wave, where if you drop a pebble in a pond, you would see ripples. It's a similar kind of thing. So look at this. If you drop a pebble in a pond, you'll see ripples. If we block out the starlight with a giant circular screen, we will also see ripples, because the light is diffracting around the edges. Now, imagine for a moment, we put a giant screen in space that's a very special shape like this, like a star shape. Then we would actually get this image here. This would be like dropping a pebble in a pond, when instead of having ripples, the area around the pebble is so perfectly smooth to 1 part in 10 billion. And that all the ripples are pushed out to the edges. And that's what we actually want to do. We want to put a giant screen in space, and that's a very special shape. But before I continue, because there are many ways to suppress starlight, we call it blocking out starlight, you actually could put this very special shape inside the telescope also. But that's a whole different story. So I'm going to talk to you now about the Starshade. And this animation shows you a starshade and telescope launching together, where the petals unfurl from their stowed position, and a central truss would expand with those petals snapping into place. Now they have to be very precisely made so that the shape of the starshade and the flatness of it and just how it stays together is a challenge. And the starshade actually would have to fly very far from the telescope, tens of thousands of kilometers, to block out that starlight just perfectly so we can find planets around it. It's called the Starshade, and the Starshade actually is going strong. And actually, tomorrow I'll be going to San Diego to an optical engineering meeting where I'll be talking there about the Starshade. But just so you know that it's a real thing, that with real hardware, I want you to see this animation. This is from August 2013, of 4 of the petals. And these petals were stowed, and now they're unfurling from their stowed position. These are longerons that actually snap into place, rigidizing the petal. There's only 4 because that's all they could afford to do. And it's mostly the place where they attach, and it's the real thing they're checking. Actually, no, what they're checking is to make sure that those petals can deploy to a position with respect to each other of millimeters, and that they can do that over and over again no matter how many times it's deployed. Now you're seeing that second stage of deployment. I always get asked, why are there people in this movie? But here, the point was to show that, not that it could deploy automatically, and by the way, later versions do deploy automatically, but that there are the petals deploy relative to each other in the same way each time. Now, what I want you to know about this central truss is it was not built just for the Starshade, actually. This is left over from constructing large radio deployables that have gone to space. Big things that the big inner disk is 15 meters, even 20 meters in diameter. And the Starshade we want to build would be about 15 or 20 meters in diameter. And later generations of this actually have smaller trusses that are more suitable for the Starshade. So the heritage from these comes from large things in space. The petals and how they stow and deploy are what is new. Here's myself and 2 of my team members, Maggie Turnbull and Aki Roberge, and here we're holding this giant petal. It has this long tip here. If it looks dangerous, that's because it is. And it's a very special shape. This particular petal was made to demonstrate that that petal could be made precisely to about 150 microns. So there's this real hardware development going on in the lab. This is a petal prototype. It says used for manufacturing tolerance verification tests. So if we can't go there, I really said that, sorry, lost track of that. If we can't go there, why look? We want to do remote sensing. We have big plans to build complicated space telescopes. The Starshade that would fly tens of thousands of kilometers from the telescope using, let's say, a 2-meter telescope is probably is most likely to be our very best option to find the true Earths. So to close, I just want to leave you with a thought. It's amazing to me that I've been working on exoplanets for 20 years. And when I first started working on exoplanets, people didn't even exist. Didn't even believe that exoplanets existed. Even the professors at my own university where I was in grad school. And the reason was because there were only a few, and they were very close to the star. And people didn't believe it because we thought that planets should be far from the star, like Jupiter is. And these big planets were found, and people just thought the star was pulsating or there was something else going on. And over the years, people started believing it. Some people started getting excited about it. But most people had never heard of it. You know, you'd sort of meet someone on the airplane. What do you work on? Well, I work on exoplanets. Oh, what's that? And now it's like, oh, yeah. I mean, of course they know. Of course they heard about it, you know, in the New York Times, or they read about it. And so you get to this point where it's incredible, but even now, all of my students, of course they're exoplanets. For children, of course there are planets in the habitable zone, actually. They learned that from that Eyes on Exoplanets thing, because they click and they can put habitable zones. And so it's incredible now. And so what my goal is, and my peers, is we want to take that one next step, actually. And we want to be able to take our children and grandchildren, nieces and nephews, to a dark site, and to point to a sun-like star, and to say that star has a planet like Earth. Thank you. Okay, thanks. Right.
Sounds like what you mean by like Earth means alive like Earth. Is that correct?
Well, like Earth has a lot of different meanings. What I personally mean is an Earth around a sun, and a planet that has oceans and continents and lush vegetation.
Will you be able to detect atmospherically things like tectonic action and stuff?
Okay, that's a really hard question. The funny thing was, before we were saying, someone suggested that our question choose the really hard ones. Okay, plate tectonics is a problem. We likely will not be able to detect any signs of plate tectonics or any gases that relate
Volcanic
thereof.
activity for sure, right?
I mean, possibly.
Okay.
Okay.
Hermione asks, what do you think of the Drake equation these days, given what we're discovering?
Okay.
And probably need to explain what the Drake equation is.
Right, well, the Drake equation was written by Frank Drake many decades ago, and he used it as a tool to illustrate what are the chances for intelligent life out there. And there are about 6 terms in the Drake equation. The first few are like how many stars form each year in the Milky Way, and it kind of moves on to how long do you think an intelligent civilization could last. And the Drake equation is still useful, but actually, myself and others have reinvented the Drake equation. And we use it for our own purposes to say, well, what are the chances we're going to find signs of life by way of gases in the planet atmosphere? But just like the Drake equation, we can only really measure the first few terms. The rest are very speculative. And so we can always kind of tweak them in a favorable direction. But we give ourselves about a 50-50 chance.
I'd say add your new equation to the presentation because you know that equation presumably will keep evolving until it's predictive. And it'd be nice to be seeing how the terms are and how the terms are changing.
Well, if and when we find signs of life, we could work back.
That would be nice, yes. Tim Rays asks, how has Earth's biosignature fared over the billions of years? Have there been periods, perhaps long ones, when we would have looked pretty dead?
Yes, good question. So oxygen, for billions of years, there was no oxygen in our atmosphere, or initially when oxygen was produced, it reacted with rocks and it didn't accumulate in the atmosphere. So for a long time, yes, our planet actually would have looked dead even when it had life.
Well, now, there was a long period of microbial life that was not putting a lot of oxygen in the atmosphere.
Right.
And that would have been undetectable by
Depends, actually. The thing is, we don't know right
spectrographs?
now. Some people think that we had a period of time when we had methanogens, methane-producing bacteria, and a huge amount of them. And they would have produced methane that would have definitely been a biosignature if there was a huge amount of it. But we don't know if our Earth had that.
Are there not planets in our own system that have a lot of methane that's presumably not biogenic?
Yes. So we have to get into a little more detail now. But some planets, okay. let's put it like Jupiter itself has a lot of methane, and any big planet that can hold on to hydrogen should have methane on it, actually. But a planet like Earth, that is so, its gravity is relatively weak, actually. It's like when you're walking around with the I'm sure this happened to almost everyone here, but if you have the helium balloon and you were a child and you actually let it go and it floated away, light gases like hydrogen and helium, they're not trapped here in our atmosphere. But on planets where they do have hydrogen trapped, if they're massive planets or cold planets, then they should also have methane. So we think we can sort through all the possibilities if we were to see a lot of methane, that we could work through the options.
So you said there's research jamming ahead on looking for other biosignature gases. Does this involve theorizing biology different than what we know so far?
That's a tough question, and right now it does not, unfortunately. I know there's a lot of fans of like silicon-based life and other things, but the reality is for astronomers, we can only see what life does. Life generates gases, it makes byproducts. We can't see what the life is, actually. And there may be a future where we can put all that together, but right now we're really just still struggling as to what we're even looking for.
So it's interesting, you said that when you finally get able to get a spectrographic analysis of an actual individual star, figuring out whether that represents equilibrium is itself an issue
For
that I hadn't
planet,
realized,
yeah.
because Jim Lovelock figured out that Mars was in some kind of equilibrium, therefore did, but he was, I guess, knowing more than you guys know about exoplanets.
He was knowing more.
Yeah.
Right.
Kevin Kelly asks, what's the future of computational optical very large telescopes, beyond phase array and various things? Are telescopes on some kind of Moore's law curve of getting insanely better every period of time?
Well, they're getting bigger and more expensive. And let me think. I got to think about how to answer that one. I'm not totally sure what his question is specifically, but we have this right now the biggest telescopes are, let's say, 8 meters in diameter or 10 meters in diameter, optical telescopes on the ground. And we actually think we've maxed out on the size we can make a monolithic mirror. So the next generation telescopes, they're 20 meters in diameter or 40 meters in diameter, and they're composed of segments that are phased together. Some of them have small segments, some have big segments that themselves are 8 meters. And so in that case, these next telescopes, it takes longer to make like the next step up, and it's just harder actually. And so it's not clear if beyond the next generation, you can still keep making segmented mirrors and telescopes. We may have to think of some whole new way to operate.
What's it going to cost for the Starshade equipped telescope?
Okay, I know you're going to laugh because I'm going to give you a very specific number.
I'm asking it because maybe somebody has it.
Okay. Good one. All right. So if we just wanted to do the Starshade itself, that is, I showed you just very briefly that we do have real hardware. We're really pushing to work on all the technology. That itself would be, including launch, would be about $650 million. And that includes reserves of about 30%. Now, that doesn't include the telescope. But the good news is we're hoping that every telescope that is launched to space will be what we call Starshade ready to work with the Starshade. So it would have a camera that could see the Starshade, the LED bank and the laser and guide on it properly, and the right kind of instrument to study the planet atmosphere once that goes. And it also have to have a radio communication to be able to communicate with the Starshade to formation fly. And there's a telescope being launched in 2024 called WFIRST. It's a 2.4 meter mirror, same size as Hubble. And that whole thing we hope is going to go far away from Earth's gravity where we can do formation flying. So our plan right now is to get the Starshade ready, push it forward, so that we have a hope of actually going with WFIRST.
Say more about formation flying. So you've got the telescope and the Starshade. They're many, how far apart?
I said tens of thousands of kilometers.
Tens of thousands of kilometers apart. And we're talking about micron precision in the petals. So this is interesting.
Yeah, manufacturing the petals. Well, it's actually 100 microns, so that's a lot better than 1 micron. But yes, Well, I can actually explain, I can tell you about the formation flying though, because it's kind of cool, actually. So what's going to happen, first I'll tell you how it will work, and then I'll tell you the part that's really hard. So essentially, when you have the Starshade and telescope, every time it moves to a new star, it has to realign. So it'll take like a week or so for that Starshade or telescope to fly across the sky and line up. And first of all, we know where the Starshade and telescope are because they're radio communicating to Earth. We can see the background stars where the Starshade is, the telescope can, so that's how it knows where it is. And then actually, when it gets closer and closer to the star, the telescope will see like a big LED bank on the Starshade. It'll know where that is. And as it's getting closer to the star, a laser actually will be used to line it up precisely. And what's the most clever thing that the engineers came up with is that once it's aligned properly, you know how it stays aligned? Because some of that diffracted light at much longer wavelengths than are being used to study the planet is actually itself used. Now, when we think of formation flying, we have had experienced formation flying and Earth's gravity docking at the space station. There's been a mission that went to the moon. It was a 4-month-long mission called GRAIL. And what it did was it did laser ranging. So they weren't tightly formation flying, but 2 spacecraft orbited the moon, and they sent a laser back and forth, and they could tell if they were closer or further. It told them the precise gravity of the moon. And so when we look at all these different situations, in thinking that the Starshade will be far away from Earth's gravity in a benign disturbance environment, we're mostly left with what we call a sensing problem. That is, can you see that laser light in that LED bank far away precisely enough to know exactly where it is to formation fly? So the story is we do have heritage, but we've boiled it down to one specific thing that we're going to be working on. Did I convince you?
Getting there. So the Starshade is its own little spaceship that has capability of maneuvering and traveling some distance, not in a, I guess are there orbital issues? Is it so far that that's not a big deal, or is it having to deal with Earth and the rest of the solar system?
Well, we want to get it far from Earth, so we could either be in what we call a heliocentric Earth leading orbit or Earth trailing orbit, or far away at the so-called Earth-Sun Lagrange point. So it has to be very far from Earth, far from the gravity.
Discover is there now, one of them, right? The Al Gore camera is at
let's see. That one would be at
Lagrange
L1,
1, I think.
yeah.
You don't want 1, you want a different one.
No, right.
Which one?
L2,
The one on the other side.
the other side,
Yeah,
right.
okay. Which is, yeah, right. Significantly farther, I forget.
Well, it just depends. You want to be in the Earth and Sun, but we don't want to be seeing like the sunlit part of Earth or having the sun
Right.
in the wrong location.
Okay. Back to a nice money question. Bill Nega asks, what area of research would most effectively increase our capability to search for Earth-like, and I'll say life-like exoplanets in the next 10 to a large number of years, if funding were not a limiting factor?
Okay, well, if it's not limiting at all, then okay, so I have to confess that with the whole TESS and James Webb setup, and even with the Starshade as the first generation, we still have to get really, really lucky, because anything we can conceive of now, even the large 30-meter ground-based telescopes, they have a good shot at finding another Earth, but they might just find 1, or 2. And we think about our own Earth. There was this good question about, well, our Earth wasn't oxygenated its whole life. It looked dead in the past, or maybe we'll find a Venus instead of an Earth. We'd really, really like in the future for someone to be able to launch a telescope that's so big and capable that it could literally find dozens of Earths. Not just 1 or 2 that we're struggling and hoping to get in our next 10 or 20 years. And so that would be very expensive, very complicated, more like a $10 billion type of mission.
Is Starshade all budgeted and paid for and coming?
No, the Starshade is not all budgeted, not all paid for. No.
Say more. What's needed?
Okay, so anything that's so new and on and forefront, you actually have to finish convincing yourself, and the rest of the world, that you can actually do it. And we have actually 5 specific problems we're working on. One is the sensing problem. We think they're all solvable. One of them, believe it or not, is that Starshade, if the edges of those petals, they have to be as sharp as a razor. If they're not, actually sunlight will bend around them and scatter off those edges, actually, and get into the image. Because remember, we're trying to block out the starlight to 1 part in 10 billion. So even things like our own sun or anything coming by, maybe even Venus or something very bright. So figuring that out. So we have this sort of list of things, and first we'd like to knock all of those things down. And that's about a $20 million price tag on that. And then to get it fully ready so that we've tested everything we can think of and we've demoed it all, and we've done also ongoing or subscale tests, like with small star shades in the lab, to show that you can really block the starlight out like you expect it to. Getting it that far is more like 150 million. And then the rest of the costs is just for building the spacecraft and the launch and things that people know how to do already.
Okay, so somebody who says, okay, I want to discover if there's life. The sequence of events is 20 million, 150 million, and then what for the actual instrument?
Let's see. More like 400 million for the rest.
400 million. Hey, this is like the biggest cosmic question we got. Yeah. The answer of we're absolutely alone, sorry folks, be very careful, would be huge. The answer of there's other life, or even lots of other life, changes everything. So, what do we say?
Kickstarter.
570 million.
Started,
Let's
yeah.
just do it. You know, I just finished reading The Martian. I'm going to see the movie with Matt Damon when it comes out shortly. Interstellar was wonderful. Gravity was wonderful. Interest in serious engaging of space is with us still, even though we're supposed to have lost interest. What happened?
Actually, admittedly, I got distracted because I was reading this question. I was thinking of how to answer the next question.
We'll come back
I like
to
that one. I like that question.
Sherry
but-
Fiddler's question.
Wait, so
It's
your
easy to
question
read.
was interest is still there?
Yeah, so maybe it's just because Hollywood loves to try to simulate zero-G, but something keeps people excited about prospects of space. You know, Star Trek is a long time ago, though. There's another round of that coming along. And these realistic space exploration by humans films keep coming along. And so I would have to say NASA's funding is not keeping up with the public interest.
Well, I think there's a few things going on. One is that I really do believe we are born explorers. And maybe it was so in the past when people were, explored Antarctica for the first time and everything. We don't have that now. We think of our oceans are not fully explored, but arguably all of land is. And I feel like space is really the place where we can still dream of exploring. It's still where things are unknown. And so that's a big thing. But also, I think in terms of the NASA and funding, I mean, one point is that things are just, you pick the low-hanging fruit, you do the easy things, you have your backyard telescope, but eventually, you're going for the 30-meter telescope, the big telescopes in space. The harder things are just more expensive.
Is there low-hanging fruit with your search and high-hanging fruit what's the difference?
Well, the low-hanging fruit...
What can you get in the next few years, and what will it take a lot longer to get?
Okay. Well, I'd say in the next few years, the test spacecraft will launch, the one with the 4 cameras, and we'll find the pool of rocky planets that we will follow up to look at their atmospheres with the James Webb Space Telescope. That's a telescope launching in 2018. If we're lucky, we may find something, but the chance of us really finding signs of life is small on that one. We hope to launch the Starshade. With that one, we can find a few Earths and look at their spectra for life. So in the next 10 or 20 years, that's what we have to look forward to.
You probably won't be surprised by a question you probably often get. Is there any science fiction reading in your personal background?
Let's see.
Well, if so, what?
I would have to admit that my favorite science fiction author, although this was really more from about 20 years ago, was Robert Heinlein. And I read all of his books many years after, so they weren't totally contemporary, because when he had written them, he predicted many things like the ATM and other things like personal robots are only now just maybe coming. But I just loved reading those. I read like everyone. I love time travel books. Recently, I started to read a new generation, or let's say genre of science fiction, including The Martian and other sort of more realistic things about going to Mars. But I'd have to say it was really mostly just Heinlein.
Say a little bit about the students you're getting these days. Do you deal with students, or are you dealing
Yes,
strictly with
we do
researchers?
students. Okay, well, there's sort of two different types of students now, and unfortunately, one of them, I don't really hate to say anything negative, but unfortunately, that's the first thing that comes to mind, but we,
That's all right. That's a good scientific
okay,
approach. And what's the
well,
problem?
I think
for
it just speaks to anyone who is a parent or, will be, or is a grandparent or an uncle or an aunt, but there's this sort of sense of entitlement that I see among some of my students, which it's not helpful. People who are, yeah. And I actually don't know what to do about it, so I'm still sort of sorting through this.
Entitlement.
Yes, because I think it must have come from like when everyone gets praised when they don't deserve it, or there's like no sense of like, I don't know, they just expect that they deserve everything, and it's not a good way to kind of go through life actually. So there's sort of that set. But there's the other set who just,
Stick with that for a minute.
Yeah.
How do you fix that?
I don't know.
How do you
I don't know.
fix that? You've got a student figures like they're already halfway there. What do you do?
I don't know how to fix that. I don't know if that problem's fixable,
Right.
unfortunately.
You don't take that student, or
Well, sometimes you don't find this stuff out until, time goes by, actually. So I've had to regroup and think through it a little more now.
okay, moving from unfortunately to fortunately, what?
Yeah, the fortunate students are just tremendously incredible, and I had a great summer with the set. I hope they're watching this, but I had a set of summer students, and it's part of a project where, we wanted to try to understand what kinds of gases could be biosignatures. But given that life on Earth literally produces thousands of, maybe let's say thousands of gases, how would you go about this? Well, some other colleagues and I had made a long list of what we thought was all molecules that could be in gas form. And so what I had the students do was see, are there spectra for these molecules? And we would get together and work, and they're just so hardworking, and they have a great sense of humor, and we just wrote a lot of code and searched through like online databases, and one of the students made a GUI, like a nice user interface, so we can look at all the spectra and compare them. And so some students are just so thirsty to work on a problem. And the ones who are really end up being suited for science, I mean, unfortunately, that image of the MIT student and professor just always working and always coding, it's true in a lot of cases. But it's that same desire when you get stuck on a problem. It's almost like reading a mystery novel, and you can't put it down because you have to get to the end. It's like that. And so the best students are ones where we're on the same wavelength, we're in sync, and we have a problem that we love working on and that we can work on together. That's the best case.
Yay. Are those spectral lines still called Fraunhofer lines?
They aren't really called Fraunhofer lines, and I believe that specifically refers to a set of lines in the sun's photosphere that were discovered by Fraunhofer.
I once handled the original slides that Fraunhofer made, the long glass slides. I broke several of them by accident. That's my contribution to astronomical history. Back to students. JR asks, how would you advise curious students to prepare for a career in exoplanetary science?
Okay, well, one thing is it seems like we can't get away from computers and programming. And I'd say programming now isn't always what it used to be, because before, we honestly coded every single thing from scratch. And we sometimes we had like a library of functions we could draw on, but now it's really I was going to say something funny, but just in case one of the students was watching it, I didn't want to say it. But now we really love using we really love using Python. I don't know if anyone here, yeah, right. Because what happens is before MIT was really big on MATLAB and other things, because they provide a license, there's like a license for students, and the sort of secret is they also have a help desk. So if the student got stuck, most of them don't know this, so you could actually email MATLAB and they would help you out. But the problem is you can't get inside of it, and it can be very slow, and it's not flexible. But now with Python, everybody's writing their own code that you can download. It's often very hard to install because you have libraries and problems with like what your computer has versus what they think you have. But the downside of that, so the great side is there's a huge power in it, because anything that you want or some complicated code that would take you, let's say, 6 months to write, it's already there. The downside is it breeds a mentality where you really just write like what we call a giant wrapper, and you just use things without thinking. And so I've seen a lot of that also. But knowing how to use code and to write code and not just to use things as what we call black boxes. I mean, that may sound a little strange of something to suggest, but I think really that's your main thing the main tool for so many disciplines today.
So there's lots of people who are coming with code training, so does that,
Yeah.
that already covers that part. Chemistry, astronomy, any things like that?
I'd say physics mostly. I mean, astronomy is really applied physics. It's great to maintain interest, but really just trying to understand the nuts and bolts is what's really important.
Jerry Fiddler asked the question that you noticed. How does your work intersect with SETI, if at all?
Right, SETI, Search for Extraterrestrial Intelligence. Well, SETI does intersect now because SETI, in addition to doing these surveys of the sky and of stars everywhere, SETI can now actually focus in part on stars with known planets. So like the Kepler 452 or Kepler 186 and those systems now. That I would say is mostly how SETI intersects.
And SETI just got a bunch of money. Does that suggest that what you're doing also should get that kind of money? Yes, it does.
Well,
No need to answer that.
I do want to answer it though, because it just suggests this, as you already pointed out, this increase in interest in space and the fact that these planets are out there. People are excited. People want to accelerate our opportunity to find signs of life, intelligent or otherwise. So yeah.
Andy Lee asks, what's the best neighborhood for exoplanets? You showed us that wonderful image of where Kepler is looking, and it's a rather small sample of a rather large galaxy.
Right. Well, I think for now, the best neighborhood really are those stars that are closest to our sun, and they're still quite far away, actually. There's about 100 stars like our sun within about 30 light years. But really, it's our solar neighborhood. We want to find things that are close because they're bright and they're easier to study. And again, because someday we hope we might find a way to go there.
So there's no particular preference of like looking, toward the center of the galaxy or away from the center of the galaxy or anything like that?
I mean, not really for me personally, but the reason why Kepler had a very specific reason for being where it is. I mean, towards the center of the galaxy, it's so densely populated with stars, it's very hard to see what's going on.
Oh, interesting.
And if you look outside the galaxy, Kepler wouldn't have had enough stars to find transits, because remember, the planets have to be specially aligned. So each different technique or each method has its own special place in the galaxy.
So Kevin Kelly asks, is there an emerging sort of taxonomy? There's been quite a while now a taxonomy of stars, and you referred to it a lot. Is there a taxonomy of planets that's emerging?
Well, when you ask that question, it's funny because we actually have, Earth. It's not too inventive, right? Earth, super Earth, mini Neptune, Jupiter, so actually, no, actually. And people fight actually about what we should call things, and everybody uses different names. But I think one thing, instead of the taxonomy yet, is what's going on, and I'll just add it in here, but we are starting to think that planets about 1.6, 1.7 times the size of Earth or smaller appear to be predominantly rocky. And planets bigger than about that appear to have like a gas envelope and be of much lower density than could be predominantly rocky.
We assume we have no life.
We assume they have no life because we think that gas envelope just isn't favorable for life. Yeah.
Has anybody got a theory of life that might function on a gas planet?
I can't think of really any great theory, but Carl Sagan himself wrote a paper actually about Jupiter. And the question is, what's really interesting actually about our own Earth is that we have bacteria floating around in our atmosphere on aerosols, little particles. And so the thought was, well, maybe in Jupiter you could have little aerosols and there's life floating around. And the reason we don't like that theory is because Jupiter has these giant convective cells. And any life, if it's floating around, it'll be brought down to where it's actually quite hot in Jupiter. And so there's no really theory for life on a gas planet, a planet with a lot of gas.
And yet in this local solar system, the only one we know well, the gas planets, some of them have pretty significantly interesting satellites around them, moons around them that may be potential places for life. Is that also an issue in exoplanets?
Well, the issue is that the exoplanets, I think I explained, were so hard to find and see. And so the moons are going to be even more hard to find and see. So we don't rule them out for any really good reason, only because they're hard to see. And any moon without an atmosphere, like Europa or something that may have subsurface oceans, we can't see subsurface life in any way. So we expect them to be out there, in fact.
Are moons of the gas, so we're detecting gas planets, we're even sort of getting imaging of them. Are their moons potentially detectable perhaps by their own transiting or things like that?
Yes, actually. So just FYI, so exoplanets are often in the news, and we always say that exoplanets have always delivered. We've gotten everything we wanted on our wish list except for one thing, and that is exoplanet moons. And everyone was hoping that the Kepler data would show exoplanet moons around giant planets, either by transit or other ways, but we haven't seen them. But they'd have to be big moons, big, like half the size of Earth or bigger.
From a distance, would we detect the moons that we have around Saturn and
No,
Jupiter? Probably
none
not.
of our solar system moons would be discoverable.
Okay, so it's another couple levels of resolution before you can get that. So you mentioned the newsworthy and problematic issue of there being more rocky planets and fewer big gas planets than were expected by theory, which is fantastic. And so where are you and others going with theory given that little problem?
Where are me and others going?
Okay, the theory was there had to be lots of gas planets, not so many rocket planets. And then the reality is there's doesn't match that.
Yeah, no, I know what you're
Now
asking.
what?
The funny thing is, what I tell my students, it's not totally true now, but when they do their PhD defense and they get asked like everything possible, I say like, look, every day is like a PhD defense. Because they get asked all sorts of things, even things that I myself aren't working on. But what I think will end up, that any way we can think of for why there are so many of these small planets, is probably it's all of the above. And so people think of things like, well, perhaps some of these planets have moved in close to the star and have just lost their atmosphere. They were maybe formed bigger, maybe like a Neptune, and started losing atmosphere because of solar wind or being heated. And that might account for some of them, but not all of them.
Are the gas giants solid inside,
We think the gas giants have a solid core, but we're not 100% sure.
including ours?
Including Jupiter, we're not 100% sure.
I'm shocked. I didn't know that. Okay. I guess really
but
dense
let me
gas
finish
looks a lot like a solid.
Let me finish the
Yes,
so,
please.
and another people think, well, perhaps this is when a planet forms, like Jupiter, we think it formed and got big, and it got so massive that it sucked in everything around it, and it became dominant. But some people said, well, what about if, let's say, in an interplanetary system, lots of them formed almost at the same time, and no one could dominate over the other? Well, they would all exhaust their feeding zone and be dwarfed. Like they wouldn't take over what the other one had because they all kind of grew up together. And so there's this variety of thinking, but it's not really clear yet which one it will be.
So you showed us one planet with two suns and presumably a complicated orbit.
It wasn't necessarily complex,
Really?
but the stars are orbiting each other,
They're
and then the
orbiting each
planet
other,
is
and these
orbiting
things
in
orbit
the
the
outer.
pair. Right,
Correct.
Okay. And like you say, sunsets there have got to be pretty exciting. Well, one of the things Carl Sagan did, and you got a glimpse of it in this long short at the beginning, is he described amazing places that were already identifiable. I know of a planet made of diamond, and you go on and these various things. Well, I want to go there. The exoticness of the kinds of places that are out there seems to be increasing and intriguingly ever more in detail. Is that what you're perceiving?
Do you mean out there for exoplanets or out there anywhere?
Exoplanets, well, yeah, sorry, not just exoplanets, everywhere. Go on.
Yeah, well, with exoplanets, it's really complicated to describe our models and how we really interpret the data and see things. And so just describing what they're like is a really kind of a tool to communicate what we think it could be. But it's probably all of the above. We imagine that one planet could be red vegetation, another one would have green or some other color even.
The variety, frankly, shocks me. I mean, this is just sort of mechanics and chemistry, not even big life. Big life makes a lot of variety. That's evolution and Darwin. That big non-life has so much variety is pretty strange and exciting in its own right. So whether or not there's things living there, once we become the things living there, these will be exotic places.
They will. But I also hope that all those planets and all those orbits brings you some, or everyone, some reassurance. Because before, Earth is definitely very special. But I think we have some sense now that it is also somewhat random because we see all these planets and all these different orbits, all different sizes and masses. And so Earth happened to be just right, and surely there should be other planets also out there that are also just right.
And different kinds of just right. The, do you want to go any of these places, or do you just want to find out if there's something pulsing there?
For me, I'm not one of those people who would volunteer to go to Alpha Cen, so I'll just stay here.
There's a pull to the places, and this is part of the SETI story. Is there a pull toward other life? Most of it's not going to be intelligent. It's going to be microbes. And do we really want to go visit microbes somewhere? The answer is yes, probably, because if it can handle microbes, it can handle other things we might be interested in. Like if you come to microbial life, to microbial Earth back when, this was a cool place to start an oxygen regime, right?
Yeah, it would have been cool. But don't forget, back in the time of the dinosaurs, they couldn't have communicated with us either.
They didn't. So you're right. They didn't even leave their DNA, we're discovering. All they left was a pattern of how their bones looked. So the lack of communication does seem to be the norm, but the lack of life is not necessarily the norm, it sounds like. And on that note, what is clear from what we've heard from Sara Seager tonight is that there's a lot happening in this century with this kind of discovery, and we're going to know a lot more about life in the galaxy thanks to you and the people you're working with. Thank you for coming.
Thank you.